So let's just review limits here real quick. I'm just going to draw a little top half of the graph. Well, here, maybe we'll put a little bit below. And we just want to draw crazy looking graph with a bunch of pieces. So let's say we've got a dot there, and then it comes up to here, and we've got a different dot here, and then it comes down, the dot here, and then continues on. But then there is, let's put a bullet there. And let's see, what else do we want? Put an open circle there. And a line over to the left. Let's call this our function, f of x. So it is a function, right? It passes the vertical line test. Anywhere I draw a vertical line, it only crosses one point. It's a weird looking function though, and so we want to learn how we would mathematically study something like this. All our functions so far have been pretty nice. Rational functions and some of the trig functions are the only ones that have discontinuities. But now we have something like a piecewise function with some weird discontinuities, but in some sense, because the function isn't going off to infinity, these discontinuities we can describe in certain ways. So we want to develop the mathematical language of how we describe them. And I started to introduce this on Friday. So let's just kind of rehash some of these things that we went over. Primarily our right and left-sided limits, as well as the value of the function, are going to be the things we care about. So let's pick 3 as our starting point. So each tick mark, let's just label as 1. Scale is just 1. And let's take a look at what's going on at 3. So remember that when we put this superscript negative, it means from the left. So the limit as x approaches 3 from the left of our function means I want to start to the left of 3 and trace the curve up until I get to that x value of 3. And the idea is, as I'm tracing, what are we approaching? What's the y value that we're actually getting close to? Not necessarily the one that's defined there. And we see that the y value we're getting close to should be 2. Sorry, my scale's a little off. Let's make it that tick mark there. And so our left-sided limit is also what we call it, is just 2. The right-sided limit we denote as 3 with a superscript plus, means I trace the curve to the right of 3. I trace it back up until the x value gets to 3. And we want to know what's the y value we're approaching. So again, we have 2. When both of those are the same, when their left and right hand limits are the same, that means the limit as x approaches 3, if we don't put a left or right, it means from both sides. And since both sides are converging on that same value, the limit is 2. This is different than the actual point that's there, though. If we ask, what is f of 2? That is asking, where is the point? That point is actually up at 3. So the limit exists, but that limit is different than the value of the function. This is what we would call a removable discontinuity. It's not continuous there, but it's just a point that's been picked up and removed and then maybe placed somewhere else. Then the other things that occur are around these points. So this is what we would call like a jump discontinuity, where it jumps from one piece to another. and likewise over here. So there we see that the one-sided limits, so the limit as x approaches, say, -1 from the left, approaching from the left, we're approaching -1 as the y value. But if I approach that from the right, then we're going to 0 is the y value. And since those two are different, since there's a jump there, the actual limit does not exist. And then lastly, if we actually wanted to find the value of the function at -1, the point is at 0. So sometimes the point matches up with one of the one-sided limits. Sometimes it doesn't. But now we have the language to describe all that phenomena. So real quick, just before we get into the IC, let's actually introduce what's going on in this IC. So the reason all this language is useful is because in calculus, we start off by studying rates of change. And what we want to know is that if I have a parabola, parabolas are useful. Anytime you throw an object in the air and let it rise and fall, or any type of falling object, the shape it makes, or the distance it travels over time, is going to be parabolic. And oftentimes what we want to compute with moving objects is how fast they are moving. What is the rate of change at a particular point in time? Mathematically, we describe this as we pick some point. And so in the IC, we're going to pick 3, 9. Our function, let's write it out, is x squared. And what we might want to know is how fast is this function increasing at the point 3, 9? And really what we're asking in that case is, what is the slope of the tangent line? So when we say tangent line, we mean I've got one point on the curve, and I just want a line that just touches that one single point and essentially fits the curve at that point, isn't going to touch anywhere else, at least in a small region. We call that the tangent line. And how do we get that? How do we discover that? What the slope is? We have a point, and we need two pieces of information for a line, right? We need a point and a direction, where the direction we describe in 2 dimensions as a slope. Well, we've seen way back at the beginning of the semester how to find the equation of a line between 2 points. So if I were to pick some other point nearby, we're just going to call it some point A. It'll have coordinates A and A squared. And then I can draw a line between those 2 points. Now, this isn't the exact thing we're looking for, but it's close. If I pick a close enough point, then the slope of, we call this the secant line between 2 points. The slope of the secant line will be pretty close to the slope of that tangent line. And it doesn't matter if I pick the point below or if I pick it above. In both cases, we're getting secant lines, and the slopes are pretty close to what we are wanting to approximate. And as I move that point, that extra point, closer and closer to this 3, 9, the slope of the secant line is going to get closer and closer to the slope of the tangent line. And so what we're going to do is approximate that and try to compute the limit. The problem with this is that, well, how do we describe the slope? The slope is rise over run, so it's the change in y values over the change in x values. And what's going to happen if I put a is equal to 3? We'll get 0 over 0. So we get one of these indeterminate forms. And so what we're going to do in the in-class activity is approximate that. Let's pick a values that are really close to 3, 2.9, 2.99. We'll make a table. So the table looks like this. This slope is going to be this guy. And so A, you're going to start with something like 2.9, 2.99. I think it goes up to like 3 nines. And then we pick other values slightly bigger. And we're going to compute the slope as I pick points closer and closer to 3, 9. And we're hopefully going to be able to get an approximation for what should go in the middle, what that slope of the tangent line should be.